I'm Reza Moini and welcome to our second YouTube video for Fortran subroutine in Abaqus. In this video, I will explain the VUGENS Fortran subroutine. So if you didn't watch our first video for VUGENS, please visit our website. So in our website, we explained the VUGENS Fortran subroutine. So it's runmodelx.com, and in here I explained the subroutine, and also I explained briefly the theory behind this shell element and the Fortran subroutine, and how you can write your own code and compile it with Abaqus. And also there's a very simple example for linear elastic material for shell element, and the code is on GitHub. So you can see the code. You can download the .imp file and also the Fortran code, so you can run it on your own computer, and then you can develop your own Fortran code. And here also there's a video, so you can watch it and follow the same step that I explained for VUGENS. In VUGENS, so it's a same concept, but VUGENS is for Abaqus dynamic explicit modeling. So in VUGENS, so again, you need to make sure that your Abaqus is working well with your Fortran compiler, and then you need to know all the input variables in VUGENS. I mean, the physical meaning of these variables you need to know, and then you need to write a very simple code for elastic shell. So for linearly elastic material, you can develop your own code, and then you need to extract your the .imp file from Abaqus. You can generate it by Abaqus, and then you need to compile this Fortran, your Fortran code with this .imp file. So it can be just for one element. You just need to make sure that your Fortran code is working well. So you need to, in fact, debug the code. So you need to make sure that the syntax of Fortran and all the input variables are correctly defined in your Fortran code, and then you need to verify the results. It's a simple case, so you can easily verify your results, and after that you are able to develop your own code. So for more complex problem for your own FE project. And if you know the final result for some specific case of your complex problem, you are able to verify result for those specific cases. For instance, for a specific boundary conditions, or for some material properties input, or some other particular case in your problem. So for subroutine, the interface of the VUGENS subroutine is like VUGENS, but here we have time, we have some other parameters. We need to define these blue font variables that I wrote, dd and de, which is the gradient of force, the force resultant, with respect to the strain. The force resultants, which is here, is force nu, and also moment nu. The force resultants in general has 6 components, 3 force resultants and 3 moment resultants. And when we have the gradient of force resultants, I mean the force vector, with respect to the strain, we have 6 and 6 matrix, the second order matrix. And there are other parameters also, state nu, internal inter nu, and also inner inalas nu. Here in this example, we are just working with dd and de and force and moment. We don't modify and we do not compute the other parameters for the simple case that we have here. Next, there are the dimensions of these input variables, so we should not touch this. And in the green font that I wrote here, this is where you can write your code, so you can write your own code to compute these input variables. The force vector, we have 2 kinds of force in our subroutine, force old and force new. We need to define force new. The force old is for the previous time increment, and we need to compute the force in the current time increment. And in the same way, for moment, we have xmom old and xmom new. So we need to compute the moment resultant in the current time increment. The DD and DDE, it's quite difficult to pronounce. This parameter is for the derivative of force with respect to the strain. So we have 6 force component, and we have 6 strain, 3 in-plane strain, and 3 curvatures. So we have a 6 and 6 matrix for DD and DE. And pay attention that this is the in the subroutine, we need to define the symmetric part of this matrix. So it should be symmetric, and we just need to define the symmetric part in the VUGENS Fortran subroutine. So this is a very simple example that I designed for to verify my Fortran code. So here we have just one element with 4 nodes. So it's a S4R shell element. The size of the element is 1 and 1. So we have also 2 directions, 1 and 2, and we have the node number 1, 2, 3, 4. And the integration point is in the center. In the initial step, I fix the left nodes in all directions, so the displacement is equal to 0. And in a step number 1, I apply a horizontal displacement to the right, at the right in the right nodes, with a displacement of 1. And the other displacement in direction of 2 is fixed. And in step number 2, I apply another displacement in nodes 3 and 4, and I fix node number 2. So this will give me a shear loading. So I will have a tensile loading, and also I will have a shear loading. So why I am doing that? Because I want to verify the computed strain for tensile and shear. So I want to make sure that in both loadings, in both steps, I have the correct computed strain and computed force resultants. So this is my Fortran code for VUGENS Fortran subroutine. So this is the interface, the input variables, and here this is the dimension. I also have here, I did not use this library, but I put it here just for your information. This is a library when you need to compute the singular value decomposition of a parameter. So in Python, it's just one line to compute the singular value decomposition, but in Fortran is harder to compute that. So in general, for me, it was always difficult to find out how to compute this simple variable in Fortran. So here I spent 2 weeks, 1 week to find out that we need to insert this library in our Fortran code, and we need also to modify some files in the directory of where you inside your Abaqus, so you can find out in internet. But here I just put it here, just for your information, if you need to have more complex computations. In the first step, we need to declare all the parameters that we want to use. So I define 6 parameters here: C11, C22, C12, D11, D22, and D12. C is for the tensile and shear, and D is for bending, so in direction of 1 and 2. And also here I did not use pi, but here it's a pi number, and also the p number. And also I need to compute 3 epsilon, 1, 1, 1, 2, and 2, 2, and also the curvature, G 1, 1, 1, 2, and 2, 2. And also the force resultants, we need also to compute these force resultants. So in the .imp file, before going, in the .imp file, you need to replace the composite section with, so this is the .imp file, so you need to replace it with a general section. So I go into another view. So this is when you generate the .imp file. So if you watch our first video for VUGENS, you can find out how to generate the .imp file. The .imp file includes all the information of your FE model, and in this model, we have 4 elements. So this is the coordinate of the nodes, and this is the element type that I used, and also I defined parameters and a material just for generating this. And here also we have the composite part. So if I search for composite, here it's the composite layup that I defined for our dummy FE model. So this part should be replaced with the part that I wrote here for the composite in this part. So here I wrote VUGENS, so here you need to replace this. So here I put C11, C22, C12, D11, D22, and D12. And these are the coefficients that I wrote in my .imp file. These coefficients will go to the Fortran subroutine, and I will save it in these parameters. So props1, it means that 1000. And here in this line I wrote 6 properties. So I wrote 6 properties in my .imp file, and I also wrote variables equal to 12. It means that I need to save 12 variables at the end of my simulation into the SDV. What is SDV? SDV in fact is if you go to step in Abaqus, SDV, here you can find out the SDV. SDV is a solution dependent state variable, so you need to turn on the SDV in your step. So this is the .imp file, and also you need to define the density in VUGENS because it is a dynamic explicit simulation, so you need to define the density, and also the transverse shear deformation, the shear stiffness, and these coefficients that I wrote here, and one is the thickness of the shell. So let's come back to our Fortran code. So here I wrote it here for debugging. So you need to print some parameters in your Fortran code, and all the parameters will be printed in the .log file. So .log file includes all the printed variables, and also if you have a problem for the compiler, so also you will have the warning or the error message in .log file. So here we need to write a for loop iteration for all the integration points from 1 to the n block. So you need so Abaqus will execute this Fortran code for all the integration points and for all the time increment. So it's quite heavy for when you have many elements. In this case, we just have one element. And here I computed the epsilon. Epsilon is equal to state old, which is for SDV in the previous time increment, and the strain increment, the derivative of strain in fact, and epsilon 22, epsilon 12, and simply I wrote n12 is equal to C11 multiplied by the epsilon, so it's a linear elastic material. So I computed the force resultants in this way, and also the moment resultants. And pay attention that this is a Abaqus dynamic explicit modeling. In the previous example in the YouTube, I solved a static simulation for linear elastic material, and here it's dynamic explicit modeling. So also we have also the density, and we are solving a time dependent problem. So here we need also to compute, we need also to write the DD&DE. So here I wrote the link for to explain the DD&DE, and I said, as I said, it's a matrix. So here I wrote all the components of this. So this is the symmetric part of the DD&DE, and you see it's go from 1 to 21, and I put almost all the components equal to 0 except the diagonal component. And here I wrote the DD&DE, the force and the moment at the current time increment for with using the force and moment that I computed here. And here I saved all the parameters that I need to know in the state new, which is the SDV that I told you in Abaqus. So at the end, I can see these parameters in my ODB file. And here I print some parameters that I told you to debug my code. So I printed epsilon11, epsilon22, epsilon12. So in the log file, so if you see, this is my time increment. This is my log file. So I have my time increment and all the computed parameters in each time increment. So in Abaqus, this is my model. So it's exactly like the VUGENS model. So it's a one element with a dimension of 1 and 1. The property is for dummy material. The assembly, it's nothing in assembly. The step, we defined 2 steps because we applied 2 loadings. And as I said, we need SDV in the field output request manager. And also in the loading, so I have 2 steps. I have 2 loadings. So in step number 1, I fix node number 1 and 4, and I apply the displacement at node number 3 and 2. And in step number 2, I release node number 4, and then I apply displacement on node number 4 and node number 3, and I fix node number 2 to apply a shear deformation. And the mesh is just, we just need to have 1 element, so the element size is equal to 1, and we have 4 nodes. And as I said, it's a S4R element, a shell element with 4 nodes. The optimization, we don't have any optimization, fortunately. And for the job here, so in job, I created 2 jobs. The first one is no VUGENS underline run model X. Just want to write a specific name for this simulation. So in no VUGENS, I just create the .imp file to have my .imp file. And in with VUGENS run model, I just want to show you, for instance, here I input my .imp file, and for instance, this is my VUGEN, and then I just write it test, and then here I import my Fortran subroutine that I told you, VUGEN example number 2 test 1. So this is, I can apply, I can insert my VUGEN's Fortran subroutine, and here I have my .imp input. And here sometime I have a problem for memory. I don't know why, but when I put as a gigabyte, for instance, like 20 gigabyte for the memory, it's working well. But sometimes with percentage of physical memory, there are some problems in my computer. Maybe you have also the problem, so just change the memory here. So here, this is the result without any VUGEN subroutine, and this is the result with VUGEN subroutine. So this is the result. So as I told you, I requested 12 SDV, so I have 12 SDV, which correspond to my force resultant. The first 3 is for force resultant. Number 4, 5, 6 is for moment resultant. Number 7, 8, 9 it's for strain, and number 10, 11, 12 is they are for the curvature that I computed in the Fortran. So here it's this is, for instance, the first component of the force resultant. And if you see, we have 2 steps. So here it's for tensile loading, and here it's for shear loading. So I have my SDV number 1, SDV number 2, number 3, number 4, and the other. So number 4 is for moment, so we don't have any moment, of course, here. So these are equal to 0, and number 7 is for our strain. So you need to verify these results. So you computed for very simple model like elastic material with a simple loading with just one single element with the Fortran code that I told you, and then you need to verify whether or not you computed correctly your output. So I hope this video was helpful for you, and wait for our next videos for the next Fortran subroutine in Abaqus.